I'm going to give you a few more examples of using the extreme value theorem to find global maximums and global minimums. Let's read through these instructions. Find the extreme values of the function and where they occur. So if you can't translate these instructions into different words, you might not know what they mean. So what about extreme values? That's going to be a global maximum, meaning a highest y value, and it also means a global minimum, meaning a lowest y value. Okay, what about this where they occur stuff? Can I get a different color? I can. What about where they occur? That's going to be the x values with the maximum and minimum. So I thought ahead this time and made more room for me to work. Now, I'm not exactly sure what 1 over x plus natural log of x looks like, but I know 1 over x is continuous from 1/2 to 4, for sure, and natural log of x is also continuous from 1/2 to 4, which means 1 over x plus natural log of x, the whole thing, is also continuous from 1/2 to 4. So I guess I'll write that. Y equals 1 over x plus natural log of x is continuous on the closed interval 1/2 to 4. So a maximum and minimum are guaranteed. Okay, and that's the extreme value theorem. So we already know we're going to have some answers here. So what do we do first? Well, a maximum and a minimum can only occur at endpoints or critical points. And critical points are where a derivative is equal to 0 or undefined. So let's do that first. The derivative of 1 over x is negative 1 over x squared. You can use quotient rule, but I'd think of 1 over x as x to the negative first power, so I could use the power rule. And the derivative of natural log of x is 1 over x. That seems weird. I'm going to combine these two pieces together by multiplying 1 over x times x over x. And I'm going to have y prime is equal to negative 1 plus x over x squared, or x minus 1 over x squared. So now we need to find critical values. Critical values are ones that make a derivative equal to 0 or undefined. So let's say let y prime equals 0. And you can probably do that in your head. We're just going to have 0 equal to the numerator. Because the first step, let's say we had the denominator x squared here, the first thing you would do is multiply both sides by x squared and get x minus 1 equals 0. So we'll just start there. By the way, let y prime be undefined. That's 0 is equal to the denominator. So over here we get x equals 1, here x equals 0. All right, are you paying attention? We're going to cross this part off. Why? Well, because 0 is not on the closed interval 1/2 to 4. So there's no way we would be using that value. Well, maybe I shouldn't cross it off. That looks crazy. But I definitely don't want to use that value. Where's my color? Red. Okay. So after we find the critical values, we're going to substitute critical values and endpoints into our function. So x is equal to 1/2. That's going to be y equals 1 over 1/2 plus natural log of 1/2. So that's going to be y is equal to 2 plus the natural log of 1/2. I'm going to write 1/2. I like that better. Okay, I hope we figure something out because I have no idea how big that thing is. X is equal to, what's the next thing we'll use? 1. Uh-oh. 1. Ooh, maybe I can zoom in. That'd be great. Y is equal to 1 over 1 plus the natural log of 1. Natural log of 1 is 0, so we just get 1. Which one do you think is bigger? 2 plus natural log of 1/2 or 1? I'll tell you in a minute. So using x equals 4, y is equal to 1/4 plus the natural log of 4. I guess that's all I can do, 1/4 plus the natural log of 4. You could get out your calculator, but I don't think you need to. Well, maybe if you know the graph of natural log of x. Let's think about that graph. Okay, so this is a point we actually already used. This is the point 1, 0. The natural log of 1 is 0. The natural log of 1/2 is going to be negative. I don't know how negative, but definitely negative. So 1/2, some negative number. And then 4 is over here somewhere. And natural log of 4 is going to be whatever that y value is. Which is at least more than 1. So I'm not really sure. I'm not certain. However, I'm going to guess that, which one do I think is the largest? I think 2 plus natural log of 1/2 is the largest, but I'm going to use my calculator. If you're thinking, well, you shouldn't use your calculator, that's all I got. And that means this was a poorly written question you wouldn't have to do on the AP test without a calculator. So this is 1.3068. Well, we know 1. And then what about natural log of 4 divided by 4? 0.34657. Okay. Let's finish up and write our answers. Don't forget, we switched pages, so I had more room to write, but we wanted the extreme values and where they occur. That's going to be a lot of writing. So the global maximum of 1 over x plus natural log of x is, oh, that's not true. The global maximum of 1 over x plus natural log of x on 1/2 to 4, there we go, is 2 plus natural log of 1/2 which occurs at x equals 1/2. The global minimum of 1 over x plus natural log of x, still on the same closed interval, 1/2 to 4, is 1/4 natural log of 4, which occurs at x equals 4. All of that stuff is my answer. And I don't think there's anything in the work that I can skip over. Okay, here we go. Another example. Find extreme values of e to the negative x on the closed interval -1 to 1. Well, hopefully we all know what e to the negative x looks like. Something like this. Without that closed interval -1 to 1, we wouldn't be able to do this problem. But, let's see, -1 over here, 1 over here. Hopefully you can tell that on that interval, actually everywhere, e to the negative x is always decreasing, which means we're going to find the maximum of e to the negative x occurs at -1, and the minimum of e to the negative x on this interval occurs at +1. But let's do all the work and make sure. So the first thing we need to do is state the extreme value theorem, y equals e to the negative x. Is continuous on the closed interval -1 to 1. So both the maximum and minimum are guaranteed. Okay, so after we make that statement, we're going to find critical values. Critical values are ones that make a derivative equal to 0. So the derivative of e to a power is e to that same power. This power is a negative x, so we also need to multiply by -1. Okay, so let's let y prime equal 0. By the way, y prime is never undefined. Well, how can I tell that? E to the power -x has a domain of all real numbers. We can put any number in for that exponent x. 0 equals -e to the negative x. Well, that's not possible. So no critical values. If you're not sure why that's not possible, let's think about the graph of -e to the negative x. -e to the negative x is a vertical reflection of e to the negative x. Okay? And this statement here, we are looking for where e to the negative x has a y value of 0. If you followed this, if you followed this thing out, it's going to get closer and closer to 0, but never actually get there. Okay? So the only place e to the negative x might have a maximum or a minimum is at those endpoints. So let's see, x equals -1, y equals e to the -1, y equals e, about 2.7, x equals 1, y equals e to the -1, y equals 1 over e, you could say about 1/3. So now we could fill these in. 1 over e, -1, e. So let's make sure to write our answers correctly. The global maximum of y equals e to the negative x is e at x equals -1, and, oh, I did it again. The global maximum of y equals e to the negative x on -1 to 1, there we go, is e at x equals -1, and the global minimum, I think I can do this, is 1 over e at x equals 1. I think I'm okay there in terms of combining those ideas together.